Time. It's the one thing we all experience, yet can never quite grasp. We feel its passage, marking our days and years. But what if I told you that time isn't as straightforward as we think? What if time, like a river, could speed up or slow down? This mind-bending concept is called time dilation, and it's a cornerstone of Einstein's theory of relativity. For centuries, we believed time was absolute, ticking at the same rate for everyone, everywhere. But Einstein shattered this notion, revealing that time is relative. It's not a universal metronome, but a flexible entity influenced by both speed and gravity. Time dilation tells us that time is experienced differently depending on how fast you're moving or how strong the gravitational pull is around you. This isn't science fiction, it's a scientific reality that's been measured and proven. So, buckle up as we journey into the fascinating world of time dilation and explore how it reshapes our understanding of the cosmos. Albert Einstein, a name synonymous with genius, revolutionized our understanding of the universe with his theory of relativity. At its heart lies a simple, yet profound idea. The speed of light in a vacuum is constant for all observers, regardless of their own motion. This might seem straightforward, but its implications are astounding. Imagine chasing a beam of light. No matter how fast you go, light will always travel away from you at the same speed, roughly 300,000 kilometers per second. This realization led Einstein to a startling conclusion. For the speed of light to remain constant, something else had to give. That something turned out to be our traditional notions of space and time. Einstein proposed that space and time are not absolute, but intertwined, forming a fabric called space-time. And just like a fabric can be stretched and warped, so too can space-time. This warping is what we experience as gravity. Time dilation arises from this interplay of motion, gravity, and the constant speed of light, leading to some truly mind-boggling possibilities. One type of time dilation is called velocity time dilation, or special relativistic time dilation. It arises from an object's motion relative to another object. Imagine two identical clocks, one stationary on Earth and the other on a spaceship traveling at a significant fraction of the speed of light. As the spaceship zooms through space, time itself slows down for the clock on board compared to the clock on Earth. The faster the spaceship travels, the more pronounced this effect becomes. This means that time is not experienced at the same rate for both clocks. While this might seem like something out of a science fiction novel, it's a real phenomenon that has been experimentally verified. Atomic clocks, incredibly precise timekeepers, have been flown on airplanes at high speeds. Upon their return, these clocks showed a minuscule but measurable difference in time compared to their Earth-bound counterparts, confirming Einstein's predictions. Section 4. Gravity's pull on time. Time dilation isn't just about speed, gravity also plays a crucial role. This is known as gravitational time dilation or general relativistic time dilation. Einstein's general theory of relativity tells us that gravity warps space-time, and this warping affects the flow of time. Imagine a massive object, like a star, creating a deep gravitational well around it. Time slows down as you get closer to the object, deeper into the well. This means that time passes slightly slower at sea level on Earth than it does on a mountaintop, where the gravitational pull is slightly weaker. The effects of gravitational time dilation are most extreme near incredibly dense objects like black holes. These cosmic monsters warp space-time to such an extent that time essentially comes to a standstill at their event horizon, the point of no return. Section 5. Time travel, fact or fiction? The concept of time dilation inevitably sparks our imagination about the possibility of time travel. Could we one day build spaceships that travel near the speed of light, allowing us to journey into the future? While the idea is tantalizing, the reality is more complicated. Time dilation does indeed suggest that time is not a rigid barrier. However, traveling at speeds approaching that of light presents immense technological challenges. Even if we could overcome these hurdles, the energy requirements would be astronomical. Furthermore, time dilation only allows for forward time travel. Returning to the past remains firmly in the realm of science fiction. Nevertheless, time dilation opens up a world of possibilities, blurring the lines between what we once thought was impossible. Section 6. Time dilation in our lives. While the most dramatic examples of time dilation involve black holes and spaceships traveling at unimaginable speeds, This phenomenon isn't confined to the realm of the cosmos. Time dilation affects our everyday lives, albeit in subtle ways. The Global Positioning System, GPS, that guides our cars and smartphones relies on incredibly precise timekeeping from satellites orbiting Earth. These satellites experience time dilation due to both their speed and their distance from Earth's gravitational pull. To ensure accuracy, GPS systems must account for these relativistic effects, making corrections to keep our navigation systems on track. Time dilation, once a mind-bending concept confined to theoretical physics, has become an integral part of our technological world. It serves as a constant reminder that the universe is far stranger and more wondrous than we could have ever imagined.